Funding for this program was provided by the Annenberg CPB project.
Additional funding provided by the people of Dow, the company that lets you do great things. The 8,000 scientists of the Eastman Kodak Company. The Exxon Education Foundation on behalf of Exxon scientists. And
the Earth is a colorful planet, whether it's seen from the depths of space or the depths of canyons, from the lush green of the tropical jungles to the subtle yellows and oranges of the deserts. We can look at our own development in many ways: music, art, ideas, technology, even color, because our use of color has played an intriguing role in advancing civilization. Much of the world we have created for ourselves came from our pursuit of the chemistry of color.
Try to imagine a black and white world. It's nearly impossible to do so. Color is such an essential part of nature. It's there in a steady background of the living green or the blue sky, or in the highlights of flowers or of birds. The complex brain, which distinguishes humans, still depends on the senses. So it's no surprise that that feature of the visible world, which gives it variety, namely color, should have entered our souls. We want color, and that's why we've brought together the plants in this garden. We describe our emotions in the red of anger and the blues. We want color on our walls. I want it in my clothing. But what is color, and how do we get it? Well, the colors of this world depend on its components, and those are molecules, incredibly large numbers of tiny particles. In the next half hour, we will show you how the search for new colors led to the age of modern chemistry, and how color in turn helps us understand the properties of the world of molecules.
People and color. The relationship is strong. Today, our world is rich with color. But it wasn't always that way. In their search for color, tribal people turned to roots and berries, insects and seashells, to the earth itself. Humans have been interested in color from the very beginning. Amazingly, it took until the middle of the 17th century to discover what color was and where it came from. Isaac Newton in the late 1660s demonstrated that white light was composed of a mixture of lights of different colors. He did it with prisms. Prisms break white light into its component colors. But why are there colors? What makes red different than violet? Light travels in waves, and each color has its own wavelength. Let's look at red. Here is the wave. The distance from the tops of these waves is called the wavelength. Now let's look at violet. The wavelength of violet is shorter than that of red. It's because light has different wavelengths that there are different colors. Until the 19th century, the colors of the rainbow weren't available to everyone. The blue indigo and red madder root, dyes used to color these Persian carpets, were derived from agricultural crops grown on plantations in India and Turkey. The supply of these dyes depended in part on the weather. The process of coloring yarn was not simple, nor was weaving the carpets. Colorful rugs like these were expensive. The same was true of clothing. Colorful fashions and carpets could be enjoyed by the wealthy, by kings and queens. Ordinary people had to settle for much less. Science historian John K. Smith of Lehigh University.
Plain people, middle of the road, average people did not wear bright colors. It was for the rich.
But there was something happening in Europe that would change all that. Machines. Mass production of textiles, of cloth and clothing, created fashion-conscious consumers. Mass production of clothing meant boom times for dye makers, but that was about to change too. Coal was the fuel of the new industrial age. It ran the mills, and when distilled, lit the streets of Europe. What was left behind as waste was coal tar.
One of the things that you had left over was a goo, a thick, viscous stuff, which had no value.
Chemists became interested in coal tar. Cheap and plentiful, it contained hundreds of unknown compounds. What was in this coal tar? Early on, benzene and more complex compounds were found to be in coal tar. Aniline was one of the derivatives. Then in 1856, an 18-year-old chemistry student named William Henry Perkin was in his laboratory at home experimenting with coal tar. Malaria was threatening British colonies, and he was trying to synthesize the known treatment quinine. He thought he could make it from coal tar.
So young Perkin was going to do a patriotic act and do some good chemistry in the process. Well, his first couple of reactions that he tried yielded nothing but brown gunk, nothing like quinine. And this is where I think, again, in all these cases, is the key step. He just didn't say, okay, next problem. He said, gee, brown gunk's pretty interesting. What's going on here?
Series demonstrator Don Showalter recreates Perkin's experiment.
At 18, William Henry Perkin was already a dedicated chemist. School was out on Easter break, but he was in his basement at home trying to make a cure for malaria. He thought that if he combined these white crystals of aniline sulfate with these orange crystals of potassium dichromate, that he would make quinine. Now, here's the way he did it. He took some of the aniline sulfate, put it into a flask of water. That ought to be about enough. And then he added some of the potassium dichromate. And he mixed it and then heated it in a warm bath. This is the old hot water bath. And he got a reaction, but it wasn't the reaction he was looking for. Instead of quinine, he got this black precipitate that came out of it. He knew that that wasn't quinine, but instead of stopping there, he was curious about this black material and wondered what it would look like, so he filtered it. We'll pour it through the filter paper. Look at this black gunk.
When Perkin dissolved the gunk in alcohol, he noticed the solution had a deep, rich purple color. He was about to make history. Perkin had made a synthetic dye, and it would be all the rage in Paris.
At about the time that he was doing his experiments with his purple dye, which the French called mauve, the fashion people had already decreed that purple was going to be the color. It was the trendy color of the time.
What was so special about mauve? As a molecule, this is what it might look like. The structure of the dye allows it to act like a molecular filter. Only certain wavelengths of light can pass through. Because silk or wool have electrical charges, and so does the dye, they stick to one another. Against his teacher's wishes, but with his family's help, Perkin dropped out of school to build his factory. A chemical synthesis like this had never gone into mass production before. The chemicals used in the lab, like aniline, were not easy to find in bulk amounts. But if Perkin could do it, others could too. And they did. Only one country had the right combination, the educational system and engineering skills needed by the new chemical industry, Germany. Industry and academia were working closely with one another. Industry was paying for research and then hiring the new students out of the universities. For chemistry, it was the beginning of industrial research and development. The payoffs were immediate.
Now, the way to find new dyes was get a large number of guys who are competently trained chemists, get them a laboratory, get them the major reagents, set them down, and say, start making things.
The path from coal tar to colorful dyes was long. There were many steps to the process, but each step produced new compounds, and the experiments began building on themselves.
You can't do a large number of experiments because every experiment that you do, you have to start from scratch, essentially. But what happens as the Germans developed the dye industry and they started making thousands of types of dyes? To make these dyes, you had to build up tens of thousands of intermediate compounds, all produced on a, rather reasonable scale. And what you have then is an enormous stable of things that you can use in experiments. And so the combinations, as the base broadens, the combinations just become infinite.
From the dye industry's stockpiling of new chemicals, whole new industries emerged. Explosives, fertilizers, and pharmaceuticals. From Perkin on, the connection between color and medicine was strong. But now scientists were able to analyze natural compounds and then synthesize them out of other compounds. Chemistry was becoming an applied science. In 1896, Bayer, a German dye company, manufactured aspirin out of coal tar. By World War I, the German chemical industry was dominant and was producing nearly all of the world's chemicals. It was the power of that industry which sustained Germany through the First World War. Even today, the leading manufacturers of chemicals are those same German companies with origins in the dye industry: BASF, Höchst, and Bayer. Now there are paints, plastics, pills, fibers and dyes of all colors, brighter colors, and colors for everyone.
The early years of chemistry were exciting ones. Not only new dyes, but flavors, pharmaceuticals, all kinds of useful molecules were readily synthesized, almost falling out of the pots of their makers. And 19th century chemists were not only good at making pretty dyes to enliven the world and to make Germany and England rich, they also turned color into a tool for advancing the science of chemistry itself. Early on, it was noted that colors change. Flowers fade, dyes bleach, or some change color when acid is added. Chemists realized that these color changes could provide information on the very reactions in which they were interested. Color could be a tool to understand the molecular world within.
How How safe is the water? How much acid is in it? How much chlorine? These are chemistry questions. And when we devise tests to answer those questions, we turn to color. There are particular dyes we use to tell us about specific substances. They are called color indicators. Swimming pool test kits, home pregnancy kits, and diabetes tests all rely on color to show their results. Some common color indicators in the laboratory test for the amount of acid in solutions, as Don Showalter demonstrates.
In these 3 graduated cylinders, I have different dyes, each of them sensitive to different amounts of acid. Now, all of them are water solutions. I'm going to add to them some dry ice, frozen carbon dioxide. And as the dry ice is added, it will dissolve somewhat into the water and increase the acidity. It'll become more acidic. Watch. We'll try the first one, which is thymal blue. A piece of dry ice. Oh, and you see the bubbling that comes from there. Again, as the dry ice produces the carbon dioxide bubbles, some of them dissolve in the water solution, and look what's happening. Oh, there's the color change. It went from that blue color to the yellow because the acid increased, the acid content, the acidity of the solution. Let's try this one. Now, this one contains the dye phenolphthalein. It's a magenta color, isn't it? Very beautiful. I'm going to add some solid carbon dioxide, dry ice to it. Again, you see the bubbles of carbon dioxide. Some of those bubbles dissolve. And look at that, it's getting lighter and lighter. And as the acidity increases, it becomes colorless. So this one changed from the magenta to the colorless solution. All right, now in this cylinder, there's a mixture of 4 dyes. Each of them now are sensitive to a different amount of acid. Now watch what happens in this one. So we start out with that beautiful purple color. Oh, and you see the blue coming in there? Because now a different dye, sensitive to a different amount of acid. There's the green, and there's the yellow. And finally, a red color. So you see the 4 different colors of the dyes, each of them changing because of the change in the acidity of the solution. So not only can we tell what is in a solution that contains an acid, but we can also tell how much acid is in there by the color change. So you can see that these dyes become a very powerful tool in chemistry for analyzing other chemicals.
If we could see a phenolphthalein molecule, it might look like this. Again, it is a small molecular filter allowing only magenta to pass through. But phenolphthalein is sensitive to acid. Changes in acidity cause the molecule to change shape, like this. It becomes 3-dimensional, and its ability to filter light is diminished. There's something else even more intriguing about dyes. At the turn of the century, sicknesses like tuberculosis, syphilis, and the flu were attracting scientific attention. Doctors and biologists searching for cures began using the new dyes to stain their cell samples so they could see them more easily under the microscope. Paul Ehrlich, a young German doctor, noticed one dye which stained only certain cells, leaving others unaffected. He had an amazing insight. What if he could find a dye that would stain only bacteria? And what if he could attach a poison to that dye? Could he kill the microorganisms without poisoning the person? This was the beginning of chemotherapy research. In 1908, Ehrlich was awarded the Nobel Prize. The first disease successfully fought with this technique was syphilis, but his dream of finding the magic bullet that would seek out and destroy all pathogens remains unfulfilled. Biologists and histologists still employ similar procedures. Certain dyes can indicate the differences between cancerous cells and healthy ones. And there are further possibilities on the frontiers of biomedicine. Research in genetics into DNA itself uses color for mapping molecular architecture. Professor Jacqueline Barton of Columbia University.
Color provides a very sensitive indicator about what's going on, about the chemical reaction that's forming. And also, we can use the color much as a stain, as a handle, to watch what's going on.
This is a compound Professor Barton uses to stain DNA. The vial on the left contains a solution of a special ruthenium compound. It glows under the ultraviolet light, but not much. The vial on the right contains the same compound and the same amount, but DNA has been added. When the dye molecule combines with the DNA, it has a brighter glow.
And the trisphenanthroline complex can bind to the DNA. Here's a structure of the DNA. This is how we imagine...
Professor Barton and her colleagues are designing propeller-shaped dye molecules that bind in certain ways to DNA.
And when it binds to the DNA, what we think happens is that one of the blades of the propeller is stacked in between the steps, the rungs of the ladder of DNA. We imagine that it's actually held quite rigidly. And if it's held very rigidly, then when it absorbs light, it will glow for a longer period of time than when it was just free in solution.
But the Dayglow dye can bind to the surface of the DNA too, like this. And when it does, it has a different glow.
They're telling us something about the local DNA structure, and so we can use them as a reporter to tell us about the local variations in that structure and how in which they're binding to that structure of DNA.
But how can we use color to tell us about the structure of DNA? The ruthenium compound is excited by a burst of laser light. This dye can bind in only two ways to DNA. It's the surface features of the DNA molecule that determine where it will bind. By measuring the different glows, it is hoped we can gain a more detailed understanding of DNA.
So for this experiment, what we're going to do is flash the sample, the ruthenium DNA sample, in a very short instant, and then watch the decay of the glow from the sample, from the ruthenium bound to the DNA complex, as a function of time. But since we're only going to flash for an instant, you may not be able to see it. Let's give it a try and see what we can see. All right. Here's the sample. Ah, there was one flash. Did you get that? All right, it's going to do it again. Okay, there it went again. Now let's see whether or not we can see what the computer's seeing in all this. Okay, so now we can see this. Here's a spectrum after short periods of time, and every 4 billionths of a second we can take that spectrum and watch the color and use that information to get dynamic information about how the complexes are binding to DNA. This becomes our probe, our way of looking in detail and looking sensitively at the structure of DNA, doing it in ways that we just can't do it with our eyes.
The next step is to design new Dayglow dyes to bind to different places of DNA and eventually build a color map of the molecule of life. It has been a little over 125 years since William Henry Perkin first synthesized dye and started a whole new chemical industry. Since then, scientists have come to a broader understanding of molecules and their structure, which Perkin could only guess at. But as our knowledge of the molecular world grows, advanced applications like staining DNA are sure to follow. These experimental greenhouses have panels with fluorescent dyes. Plants need red or blue light to grow. The dyes on these panels take green light and turn it into red light. This helps the plants grow faster and be healthier. Even more exotic experiments are underway. Dyes might make solar energy more efficient. The dyes in these solar panels direct the sunlight to the edges, which are lined with solar cells. This means fewer cells are needed to generate electricity. Increased crop yields to feed an ever-expanding population, and electricity from the sun, and unraveling the mysteries of life itself, all with the chemistry of color.
We have seen the relationship between color and the world of chemistry. Color is not magic. In there are molecules absorbing and reflecting light. And chemistry is the science of those molecules. Because it is a science, common sense, good hard facts, and logical thinking count. But so does intuition, and so does serendipity, the accidental discovery, a clever mind like that of William Henry Perkin to follow it up. Perkin was prepared for what he did by study with the great German chemist August Wilhelm von Hofmann, no relation to me. And what Perkin did was not in a vacuum. Within a space of just a few years, several groups of German chemists were competing effectively with him. The German firms organized research teams to take basic knowledge into practical applications. For instance, to make a dye that could surpass natural indigo. The elements of the story, education, a chance discovery, its exploitation, collaboration, and competition, these are the hallmarks of modern chemistry. But most important, chemistry is a quest, a search for understanding of the molecular world around us. It's an exciting search. Think of Perkin when he first made that dye, and then by changing the reagents, if he could get a different color. And you could feel Dr. Barton's excitement as she probed the ways to map out DNA with color. We will learn more about our molecular surroundings as we explore the world of chemistry.
Funding for this program was provided by the Annenberg CPB project.
Additional funding provided by the people of Dow, the company that lets you do great things. The 8,000 scientists of the Eastman Kodak Company. The Exxon Education Foundation on behalf of Exxon scientists. And